Alright, in this lesson we're going to start talking about the other major part of calculus. So we've used derivatives up until now, and that's with differentiation, and here we're going to do the antiderivative. So the derivative that we've been using is telling us the slope, and we're going to see that the antiderivative is going to give us area. And we saw that in the beginning when we approximated. We looked at position, velocity, and acceleration, and to move up the levels we did the antiderivative, and to move down we did the derivative. So here we're doing antiderivatives, and let's start by thinking about find an equation that has this for its derivative. So here's the result of using the power rule. So what could the original equation be? Well, it could be that. The derivative of this is 2x. But not only could it be that, it could be this. Or it could be this. And we see that you could have any constant, because the derivative of the constant is 0, so it doesn't matter. And what we end up writing is that. And here's some new vocabulary to go with this. All of these equations are called particular solutions. So that's called a differential equation, and here these are particular solutions of the differential equation. This is called the general solution. So we have particular solutions and then a general solution. So general solution will always be generalized. The constant is not a specific constant, it's a general one. We can also write y equals 2x. The differential equation could be written like this, or we could even write it like this. So they all can be used, each notation. And what we're doing is when we do the antiderivative, we are finding the equation that has the given derivative. We have a power rule. The power rule for antiderivatives, if the derivative is ax to the n, then the original equation is going to be like this. We start with the same a and x, but now we're going to add one. When we do the derivative, we subtract one, but now we're going to add and divide. And that's the power rule for antiderivatives. All right. So here we have a differential equation. And we will multiply both sides by the differential of x. When we talked about in chapter 3, we had differentials. That's the differential of y, the differential of x. Multiply by both sides by the differential of x. And this allows us to use integral notation. So that's a skinny, stretched out S. Integral notation. So with integral notation, we anti-differentiate, we integrate, we find the antiderivative, find the indefinite integral. So a lot of synonymous vocabulary. You want to make sure you know all these words because a question might have one of these words, and if you don't know what it means, you won't know that it's just a simple procedure. All right, we're going to do the antiderivative of dy. So that's y. The antiderivative of 1 is what we're doing. The antiderivative of 1 is y. So we're asking, 1 is the derivative of what thing? It's the derivative of y. Here we have 3x squared is the derivative of what thing? And we're going to go like this. If we want to show all the steps, we can write it like that, just like we saw in the previous explanation. And we always have a plus c there. So now we have x cubed. 3 divided by 3 is 1. And we're done. If you want to check this and you take the derivative of this is 3x squared plus 0. So it takes you back there. And pause the video, try that problem. So we want to make sure we rewrite it as dy dx equals 4x cubed. And then we separate the variables. We want everything with an x on the right, everything with a y on the left. And we'll integrate. Here we're going to add 1, divide by that number, and have plus c. So we get y equals x to the 4th plus c. This is the general solution of that differential equation. Okay, so we found a general solution. Now let's find a particular solution. To find a particular solution, information about the solution has to be given. That's called the initial condition. So we're going to rewrite this. And that's called Leibniz notation. The name doesn't come up very much, so you can do well without it. separate the variables. And we're going to do the antiderivative of this. Add, divide, and here we have a 1. So we're going to add, divide, and then at x equals 1, y equals 3. That's the initial condition. So we need a particular solution. We need to know what number goes here. So we're going to take this equation and put a 3 in place of the y, put a 1 in place of the x, and solve for c. So we have y is 3. 3 equals, that cancels, and we have a 1 cubed. 1 squared over 2 plus c. We're replacing the x's with a 1. So that's going to be 3 equals 1/2 plus c. Subtract a half, and we'll get 3. Okay, there's a 1 there still. 1 cubed, so 1 plus a half. So we have 3 halves. And we're going to subtract 3 halves, so we get 3 halves equals c. And now we know the particular solution is x cubed plus 1/2 x squared plus 3 halves. Here's another problem. Find the particular solution of that differential equation. Pause the video and try that. So let's separate the variables, integrate. We're going to add and divide. 3 plus 1, then divide. 1 plus 1, then divide. And we'll always put that. Oh, and the c is called the constant of integration. That's the vocabulary going along with that. Okay, and then at x equals 0, y equals 1, we're going to take that equation and put a 1 in for the y, 0 for the x, so we get c equals 1. And the particular solution is this with a 1 right there. Alright, let's do more of that. Just use some radicals and make sure we can do it with radicals. Alright. Find a particular solution with the initial condition 0, 2. So we want to write it as dy dx, x to the 1/2. If we're going to do the power rule, we want to have that fractional exponent. And we'll multiply by the differential of x. We're going to integrate. And we're going to add 1 to a half. Remember that half plus 1 is a half plus 2 over 2, 3 over 2. And here we have 1. If you think of a 1 as being 1x to the 0, then you can think, okay, 0 plus 1. So this has x to the 0. We're going to go 0 plus 1, so that's x to the 1 over 1 plus c. Dividing by 3/2, we could just multiply by 2/3. And then we use the initial condition. So we'll have y equals 2, x equals 0, c equals 2. So the particular solution and just put the c equals 2, so we have a 2 there for the particular solution. Okay, and initial condition is 1, 3. Alright, pause the video and try that one. Okay, we need to multiply both sides by the differential of x. We're separating the variables. Integration. So we're going to go 1/2 plus 1, 3/2 over 3/2. So we add 1 and then divide by what we get. Here there's a 1, so we're going to add 1 and divide. And then the constant of integration. 3 times 2 over 3. Dividing by 3/2, let's multiply by 2/3, x to the 3/2 plus 1/2 x plus c. We can cancel that, and now we solve for c using the initial condition. So y equals 3. And now we have 2 times x plus 1/2 times x plus c. So that'll be 2 plus 1/2. 2 1/2, let's say that's 5 over 2. And then this is 6 over 2. So 6 over 2 minus 5 over 2 is 1 over 2. And we get the particular solution, 2x to the 3/2 plus 1/2 x squared plus 1/2 is the particular solution. Almost done. We'll just do a couple trigonometric functions, and that'll be it. So we have a differential equation with initial condition we just use the same strategy, dy dx, and we'll multiply by the differential of x. Integrate. When we integrate, we can have put any constant factor on the outside. So if you wanted to do it that way, you could, but I think we want it on the inside anyway. Alright, so over here we get that. And let's just think of this negative as being with negative cosecant squared. Remember that the derivative of tangent is secant squared. So the derivative of cotangent is negative cosecant squared. They have that pattern there. When you do the derivative of a cofunction, you also put a negative on there. So we have this already, and we can see that the antiderivative is just going to be cotangent. Then we'll use the initial condition. Y is 1. Cotangent x is pi over 4. And we know that at pi over 4, cotangent is x over y, so it'll be 1. So the constant is 0. And the particular solution is just cotangent x. Last example, pause the video and try that one. Find the particular solution using this initial condition. Multiply by dx, integrate both sides, and cosine is the derivative of what thing? Well, let's see. The derivative of sine is cosine. That's the one we want. We have this, and we're going back to that. So the antiderivative of cosine is sine. Then we'll find the solve for c using the initial condition. Y is 3 equals sine of pi over 2 plus c. Sine of pi over 2 is 1. C is 2. And the particular solution is sine x plus 2. Alright, and we'll stop there.